Okay, welcome to the week 7 session of the problem solving sessions for the NPTEL. This is for structural analysis 1. I'm Prithvi, I'm a PhD scholar from IIT Hyderabad. So far we have actually uh, analyzed the structures which are statically determinate. So statically determinate structures, we can use the force equilibrium and also again the equilibrium equations to solve for the support reactions, as well as we also found out the deflections and rotations of the statically determinate structures. From this week onwards, that is week 7 onwards, week 7 to week 12. So again, another 6 weeks we'll be discussing about the analysis of statically indeterminate structure. So most of the structures which usually we come across at various constructions, and also most of the structures are basically statically indeterminate structures, except for a few, such as the bridges are kind of statically determinate structures, most of the bridge girders and all. But rest of the things, they are statically indeterminate structures. So the only difference for the statically indeterminate structures is we also have an added compatibility conditions, and also the constitutive relations. So we have compatibility conditions and constitutive relations in addition with um, the uh, equilibrium equations to solve to solve this to solve for to solve the statically indeterminate structure. So let us just I'm just trying to write. I think my screen got stuck. Just a second. Yeah. Just a minute. I think there is some issue with my writing pad. Let us have some basic points regarding the statically determinate structure. So before that, before I connect it, let me just please wait a minute. Just wait a minute. I'll get back. I'll come back. Hello. Yeah, Vidyaji, give me a minute. Actually, there is some issue with the iPad. I'll just maybe give me a minute. I'll just come back. Okay?
Definitely, definitely. Take your time.
Sure, sure. Thank you. Before we start working some problems, we'll just go through some of the concepts behind the solving of the statically indeterminate structure. So you can see basically, we have different types of structures. So there are two different types of structures: statically determinate and statically indeterminate. So again, like I said, the statically determinate are easy to analyze. So because we only require some equilibrium equations to solve for the support reactions, and also to, it is enough to find out the member forces. So the member force, that means that we can, if it is a frame member or if it is a beam kind of a structure, so we can find the bending moment, shear forces, and also the axial forces. And when it is a time member, or an axial members, like the truss member, so the member forces are axial forces. So we only require a few equilibrium equations to find out these member forces. But when it comes to the statical indeterminate structures, again, there is some complexity involved. So complexity, like we need to have some compatibility equations. So maybe we can discuss about this compatibility equation when we are trying to solve some questions. Um, and also sometimes we also use the constitutive relations. But in this course, we'll be mostly discussing about how we make use of the compatibility equations to solve the statically indeterminate structures. So if you can see in this, we have x, y, z. So we have three different coordinates. So again, for a coplanar member, so let us say if it is a coplanar members, we have three different types of equilibrium equations. We have the forces in x direction, forces in y direction, and the bending moment will be along z direction, right? So for a beam member, we have a bending moment which is about z axis. So we have three different types of equilibrium equations which we use it, and we call it as sigma fx equal to 0, sigma fy equal to 0, and sigma mz equal to 0. So only then the forces are equilibrated, and only then, the structure is stable, right? So again, we have seen this kind of questions in our first when we are trying to solve the initial in our initial sessions. So I'm just skipping it. So you can see in static indeterminacy, what happens is that, if you can see in the first question, it is called as a propped cantilever, right? So we have a fixed support at the left, and also we have a roller support at the right, and we have a point load which is acting at the mid span. So we have three equations. We have three unknowns here. The three unknowns are bending moment m at the fixed support, and the vertical reaction p at the fixed support, and this horizontal and this roller, it can also offer a vertical reaction, but it cannot offer any horizontal reaction, because in the horizontal reaction it can move, right? So where it cannot resist the forces, because it is a roller, so it can move in x direction, so there is no resistance coming in that direction. So we have three unknowns, p1, p2, and m. So how many equations do we have? So we have sigma fx equal to 0, sorry, sigma fy equal to 0. Again, this is a planar members, right? So we have sigma fy equal to 0, and we have sigma m equal to 0. So we have only two equations in this case. If we have this if we have this load which is acting vertically, if it is acting inclined, right? So we will also have an extra reaction which is in x direction, horizontal reaction at the fixed support. So in that case, we'll have four unknown reactions, and we'll have three equilibrium equations. So so that is 4 minus 3 degree of static indeterminacy, we call it as, and that is 3 minus 4 minus 3 is 1. So 1. So we need one is a degree of static indeterminacy. So that for finding out that unknown force or unknown reaction, we may require a compatibility equation. So we'll solve some problem. We'll solve the same problem using these compatibility equations, and let us find out how we are making use of the compatibility equations. If you see in the second one, this is a frame member. It is a frame structure. So both sides pin connection. The pin connection can have one horizontal force and also a vertical force, right? The moment here is 0, so it's a pin member, so there is a movement release here. So when we have such kind of things, you can see there are four unknowns, and we have three equilibrium equations. So in this, it doesn't matter where the load is acting, because at any cost, it always develops two types of forces, x in x and y direction, right? So we have one, two, three, four unknowns, and we have three equilibrium equations. So sigma f x equal to 0, sigma f y equal to 0, and sigma m equal to 0. So we have 4 minus 3, that is 1 static indeterminacy. So 1, which is unknown, that has to be found using the compatibility equations. So similarly, we have kinematic indeterminacy. That means how many degrees of freedom that the structural member has. So maybe we can wait for this. We'll try to discuss this in the coming, maybe in the coming lecture. So let us first solve for the static indeterminacy. Let us first understand the static indeterminacy and solve these members using the flexibility method. So we can solve the questions using the flexibility method, and then we can solve some static indeterminate structures using the same method. So I think now my I had okay, now my iPad is, I think it is back. I just switched it off and I just switched it on. So I think we can start solving the problems. Let me share my screen again. Yeah, yeah. I hope you can see my screen now. I can see my screen here in my another monitor. Yeah, I think it is visible now. So yeah, we're good to go. We'll just start the session. We'll just start solving some problems on how to find out the um, how to find out the support reactions for the determinate beam members. We'll start from a simple problems like the prop cantilever, and then we'll just solve one frame members also in the same session. So let me start with a small prop cantilever. So we have a prop cantilever. As you can see, this is a prop cantilever, um, and P load is acting at the mid span. Let us name the supports A, B, and let us also say this as C. This doesn't look like it's L by 2, but let me write it as L by 2. L by 2. Yeah, this is the question. So again, the solve for the support reactions at B. It seems like we have. Let me first solve for the we'll just see the free body diagram. So what do we have here? We have bending moment M. We also have the shear force. So let us call it as force VA, and we have VB. So number of unknown number of unknown reactions or number of unknown forces are three. Okay, in this case. So like I mentioned previously, like for example, if you have load P acting something like this, so it has two components, right? One horizontal component and one vertical component. In that case, you may also have a horizontal force developed in at support A. So now that is not the case. So in that case, you'll have one extra force here, and also we'll have one extra compatibility. Sorry, one extra equation of equilibrium. So right now the case is simple. It is vertical force of P acting at the mid span, and number of unknown reactions are three. So number of equilibrium equations available. equilibrium equations available are only two. So those are sigma Fy equal to 0 and sigma M equal to 0. Okay, so we have two. So ds, this is actually static indeterminacy. Static indeterminacy. ds is 3 minus 2, that is 1. So static indeterminacy is 1. So we need one more in addition to the two equilibrium equations, we require one extra equation that is called the compatibility equation to solve this type of question. So again, just a recap of what the force method or the flexibility method. So again, it is developed by the Maxwell, James J.C. Maxwell in almost around like 1800s, 1864. Later, it was again refined by the Otto Moore and Muller-Breslau law. This is also called as the compatibility method because we will find out the compatibility. I'll explain. I'll explain what is compatibility is, and again the redundant forces. So this is the redundant force, right? So one, this force is actually we can't find this force directly. So this is called the redundant force. So the redundancy. So this redundant force is actually found out by the compatibility equations. So again, what is compatibility? So usually what happens in this case is we'll try to tweak it. We'll try to tweak and we'll try to divide the same question in terms of two determinate structures, and we'll find out a common point where we'll make use of the compatibility equation. So for example, the same structure, let me draw again. So we have the prop cantilever beam. So this is the prop cantilever beam, right? So this I can actually, what I can do is uh, I can actually draw this in this way. So I can draw it as a cantilever beam plus another cantilever beam, all right, but with a force Pf. This is unknown force. What I'll call it as Vb because I have already called it as Vb. So can I do this again? What is the point? Actually, what is the theory behind doing this kind of things? Because as we discussed from the beginning of our course, we are actually discussing about the members which are elastic, right? So what does elastic means? And we also say that the superposition principle is valid. So the superposition principle does, it means that whatever you have, let us say you have a load, you have a beam something like this, maybe a fixed beam. Sorry, or else let me take a let me take a simply supported beam. So we have a simply supported beam. Let us say we have a load 5 kilonewtons or maybe 10 kilonewtons. So what does superposition mean? Superposition means that this can be, you can, you can just buy, you can divide it into different types of 5 kilonewtons plus 5 kilonewtons. So it is not going to make a much deal. So we always like when we start formulating or when we start learning the theory behind the analysis of the structure, we always have the important assumption saying that the structure is inelastic. In the structure is in elastic range, within elastic range, and the superposition principle is valid. So that's what the major assumptions of the structural analysis is, right? So and also we also say that the supports are not settling, the temperature effects are negligible. Anyways, we can actually include that when we are also analyzing it for the support settlement and all. But right now, let us fix to one point that fixed support is always fixed. That means there's no support rotation, there is no support, there's no support rotation. Also, there is no support settlement in this case. So we can actually break our structure in this way. So the same prop cantilever beam we can actually analyze by actually breaking down into two different types of cantilevers, one with the load P and another one with the unknown force. In this case, I have chosen unknown force VB, and then we can like break down into two things, and I'll just name it as B. Right, this is B, and this is B. Now comes the trick. So what is compatibility, right? So in compatibility, I'll call this member. I'll call this one as structure one, sorry,
So I'll call this member as
I'll call this member as this as
let us say beam 1,
let us say beam 1,
and I'll call this
and I'll
as
call this as
beam 2,
beam 2.
and I'll call this as beam
Yeah,
2.
I'll call this as beam 2.
All right. So we have beam 1 and beam 2. Now let me redraw the beam
Alright.
1 again.
So we
So we
have
have
beam 1
beam
and
1,
beam 2.
which is
Now
a
let me
cantilever
redraw the beam 1
with
again.
load
So
P
we have beam 1,
A,
which is a
A.
cantilever
This is
with
beam
load
2.
P,
Again we
A,
have a cantilever
B. This is beam 1.
unknown
Again we
force.
have a cantilever
I'm applying an
with
unknown
unknown
force
force VB. I'm applying an unknown force VB,
V.
and this is
So
A,
in this, what I'll
B.
try to do is
So in this, what I'll try to do is I'll try to find out
vertical
vertical
displacement. I'll call
displacement. I'll
vertical
call
displacement.
vertical,
Let us
like
say
let us
this is
say
going to
this
bend
is
something
going to
like
bend
this.
something like this.
So this vertical
So this
displacement I'll
vertical
call it as
displacement I'll call it as
delta.
delta.
Uh,
Uh,
this is 1, right?
this is one, right? Delta.
Okay, I'll call
Okay,
it as
I'll call
delta
it as
B.
delta B.
And in this
And in
case,
this
what
case,
happens?
what happens? The vertical displacement is something like this.
And I'll
And
call this
I'll
as
call this as
uh,
uh,
maybe
maybe we can call
small delta B.
small delta B, something like that.
So
So
with VB
with
as
VB
unknown,
as unknown,
VB
so
we don't
VB
know,
we don't
right?
know,
VB is
right?
actually
VB
an
is
unknown
actually an
force.
unknown force, right? So
With I'll
with
take
I'll
VB
take
as
VB
VB
as
itself,
VB itself,
but T is
but T
something
is
which is
something
known.
which is known.
That is
That
what
is what
the
the
input is, the
input is,
load which
the
we know.
load which we know.
Because of this
Because
P,
of
we'll
this P,
find out
we'll find
delta
out
B.
delta B.
So delta
So
B is
delta
how
B is
much?
how much?
And because
And
of
because
VB,
of
so
VB,
I'll
so
find out
I'll find
delta
out
B
delta
in
B
terms
in
of
terms
VB.
of VB.
So delta
So
B is
delta
how
B
much?
is how much, right?
This will
So
be
this will
in
be
terms of in terms
in
of
terms of
VB.
VB,
Okay,
okay,
vertical force
vertical force
at
at
node
node B or at
B.
point B or at support B.
So
So
again, what is the
again, what is the
compatibility?
compatibility?
So what's the
So what's the
compatibility?
compatibility
So
mean?
this
So
is
this
a
is a
roller support.
roller support.
So
So
in the roller
at the roller
support,
support,
it should not
it should
have
not
any
have any
vertical
vertical
displacement.
displacement or vertical deformation or the vertical displacement at that support, right?
It can only
It can
have
only have a
rotation.
rotation there.
So
So what I'll try to do
do is
is
I'll make
I'll make
delta
delta
B
B
plus
plus
delta
delta
B
B
equal to
that is
0.
equal to 0.
So this is
So
my
this is
another
my another
equation.
equation.
This is
This is this
my
is my
compatibility
compatibility
equation.
equation.
All right.
All right.
So now we
So
have
now we have
sigma
sigma
Fy equal
Fy
to 0,
equal to 0,
sigma
sigma
m equal to
M
0,
equal to 0,
and also
and also
compatibility
compatibility
delta B equal to
delta
0.
B equal to 0.
So we have
So we have three equations,
three unknowns.
three
So it can
unknowns.
be
It
solved.
can be solved. So we can solve the unknown equation.
So let's
So
solve this
let us
question.
solve this question.
So again,
So again,
I'll
I'll
draw
draw
beam 1 and
beam
beam
1
2.
and beam
So
2.
let us
So
solve
let
for
us solve for
delta B.
delta B.
Delta B.
Delta B.
So we have a
So we have a
cantilever beam
cantilever beam
with
with
point load
point
P
load P
at L by
at L
2
by 2,
A
A,
B.
B.
So
So
for
for
solving
solving delta B, we
use
can use
various
various
equations.
equations. So for now, what I'll try to do is I'll try to use um, maybe we can use moment area method, or we can use the energy methods and all. Let me solve it as using moment area method, because that is that is what we are more comfortable with, and also
It is
it is uh,
easy
it
to
is
solve
easy
in
to
that
solve
case.
in that case also, right? It's just a cantilever beam. So uh,
What
what, like,
let
for
us
this, let
solve
us
for the
solve for the
support reactions.
support
So
reactions.
we'll
So
have
we'll
P.
have P directly here.
So this is
So
L
this
by
is
2.
L by 2. This is L by 2.
So
So
it
it
will
will
generate
generate
an
an opposite force. Sorry, in this direction. Sorry,
it will
it will generate an opposite force in this direction,
which is
which is
PL by
PL
2.
by 2.
Bending moment
Bending
is
moment is
PL by
PL
2.
by 2.
Now let
Now
me draw
let
the
me draw the
BMD
BMD,
bending moment
bending moment
diagram.
diagram.
So we
So
have
we have,
this will also
this
be
will
an
also be an kind of a
recap of
recap of
the
the
moment area
moment
method.
area method.
So this is
So
my
this is
bending
my
moment
bending
diagram.
moment diagram.
PL by
PL
2.
by 2.
Here it is
Here it is
0.
0.
So
So
how do we
how do we
find
find the
the deflection
deflection at
point?
this point?
So we
So we
have
have
something like
something
this.
like this.
Okay.
So this thing
And this.
and this.
But
But
after
After this, actually, this is going to be linear, right? There is no there is no
bending moment in
bending
this.
moment in this. So
Here it is
here it is
non-linear.
non-linear.
The
The
deformation is
deformation is
non-linear
non-linear
in
in
this
this
zone AC,
zone AC,
and after that C to
and
B it
after
is
that
linear.
C to B it is linear. It is going to be linear because
There is no bending moment
there
acting
is no
there.
bending moment acting there, right?
So
So
what we
so
can
what?
do,
Yeah, let me.
so for
So
this
for this to find,
first
first
I can
I
find
can
this.
find this.
So I'll
So
call
I'll
this
call
as
this as
delta 1.
delta one,
Okay,
okay,
and then this is
and then
delta
this is
2.
delta two.
So
So
this is delta
this
1.
is delta one.
So delta
So
1
delta
plus
one
delta
plus
2 is
delta two is going to be
delta B. This
delta
is what
B.
we need
This
to
is
find.
what we need to find.
So to find out
So to
delta
find
1,
out delta one, what do we
we
need
need
to
to
do?
just
We need
take
to
the
just
moment
take
of
the
this
moment of this
M by
M by
EI diagram.
EI diagram,
So bending
M
moment
by EI. So bending
EI
moment
diagram
by EI diagram
at this point, right?
at this point, right?
So
So
delta 1 is nothing
delta
but
one is nothing but
half
half
PL by
PL
2
by
EI
2EI
times L by 2
times L by 2
2
times
by 3
2
times
by 3
L
times
by 2.
L by 2,
So
right?
yeah, this
So
is
yeah,
my
this is
centroid
my
from
centroid from here.
2 by
2
3
by
L.
3 L.
So what do we
So
get?
what do we get? We get
Something like
something like
PL cube
PL
by
cube by
uh, 6 6
3,
12
6, 12,
24.
24.
Yeah,
Yeah.
PL
PL
cube by
cube by
24
24
EI.
EI.
So what about
Now what
delta
about
2?
delta 2? Delta 2
Is again easy.
is again easy. So
This is nothing
this is
but
nothing but you have a slope here, right? You have some slope here.
so this
So
slope
this slope
times
times
this length.
this
This is
length.
L by
This
2.
is L
This
by
is
2.
theta.
This is theta.
So how do we
So
find
how do we
theta?
find theta? Let me go to the next page.
So
So
theta
theta
is equal
is
to
equal to
area of bending
area
moment
of bending
diagram.
moment diagram.
Area of
Area of bending moment diagram.
I mean
I mean it's flexure diagram BMD by EI.
so half
So half times half
times
times
PL by
PL
2
by 2
EI
EI
into
into
L by 2.
L by 2.
So this is
So this is
PL
PL
square by
square by
8
8
EI.
EI.
Now delta
Now
2 will
delta
be
2 will be
this is nothing
this
but
is nothing but you can
tan
see
theta
tan theta is nothing but delta 2 by L by 2.
so tan
So
theta
tan
can
theta,
be
can we assume that the rotations are
very small,
very small. So tan theta is
approximately equal to
approximately
theta.
equal to theta t.
So delta
So
2 is
delta 2 is L by
2
2
times theta.
times theta.
That is going to
That is
be
going to be PL cube by
16
16
EI.
EI.
Okay.
Okay.
So once if
So
it is
once if it is
16 EI,
16
then what
EI,
is
then what
delta
is
B?
delta B?
Delta B is
Delta
nothing
B is
but
nothing but
delta 1 plus
delta 1
delta
plus
2.
delta 2
PL cube
PL
by
cube by
24
24
EI
EI plus
PL cube by
PL cube by
16 EI.
16 EI. This is
Turning out to be
turning out to be
1648.
1648. Yeah, 48.
2 plus 3
2 plus 3, 5.
5
5
PL cube
PL
by
cube by
48 EI.
48 EI.
So delta
So
B is
delta B is
so and so.
so and so.
Now, what is
Now,
the next
what
one?
is the next one?
What is the next one?
What is the next one?
Small
Yeah, the
delta B.
small delta
Small
B.
delta B.
Small delta B. We need to
Small
find the
delta B.
small delta B.
Small delta B
Small
is
delta B is nothing but
delta B
delta
because
B
of
because of
VB4. So
VB4.
in
So
this,
in this,
you can see
you
here.
can see
This is
here.
in
This
terms
is
of
in
P.
terms of P. So this is known, no, known because that is the external force.
So
So
small delta
small
B is
delta
how
B is
much?
how
Is the
much? This
question.
is the question.
For this,
For this,
what we can
what
have
we can
is
have is we can
we can have
again
the
we can
same
have the same cantilever beam.
we can have the
We can
same
have the
cantilever
same
beam,
cantilever beam, and then we can
we
apply the force VB.
can apply
We
the
can
force
apply the force
VB.
VB.
So we have
So we have
deformation
a
profile
deformation profile, deflection profile, something like this.
simply to
So
delta.
this is delta B.
So what are
So
my
what this is L.
so what are my
So what are my
reactions?
reactions? So this is in this direction. So
It has to
it
be
has to,
yeah.
yeah.
This is
This is V
VB
VB
times L.
times L.
Okay,
Okay,
and this will be
and this will be
downwards.
downwards.
How much?
How much?
VB.
VB.
So
So
again,
again, the display, the bending moment diagram is similar.
VB
VB
times
here and zero somewhere here. Let me draw it correctly. So this is VBL
yeah.
here and zero here. So this
L.
is L.
We want
We
to
want
find
to find
displacement here.
displacement here.
So we
So
know
we
the
know the
slope at this
slope at
position
this
is zero.
position is zero.
So
So
what is
what is displacement in moment area diagram? So it is The intercept is nothing here. The intercept is directly the displacement. The intercepts are nothing but the moment of the area at the point of interest, right? Moment of the area at the point of interest. So this is my point of interest. So this is my area. This is L. So delta B is going to be half VBL times L times 2 by 3 L, 2 by 3 L. Okay. So this is going to be VBL cube, VBL cube by 3. Sorry, EI. M by EI diagram, right? EI. So VBL cube by uh, 3 EI. So this is actually a very standard equation, right? For usually for a point for a cantilever at the ends of for a cantilever at the free end, when we apply a when we apply a load point load P, the displacement there is PL cube by 3 EI. Likewise, for a simply supported beam, when we apply uh, a UDL, so the maximum displacement is like 5 by 384 WL power 4 by EI. And we also have P by 48, no, 5 by 48. Yeah, when we have a point load, something like that. Yeah, I think it is, yeah, something like that. So we have delta B is VB L cube by 3 EI, and capital delta. So this is 2, this is 1. So what is the compatibility? We were discussing about this, right? Anyways, you can understand this is actually in vertical direction, right? So delta B is going to be vertical when we consider it is in this direction. But you know that delta B should be equal to capital delta B should be equal to small delta B. So I'll just equate them here. So what I'm trying to do is delta B is equal to delta B 5 by 48 P L cube by EI should be equal to now VB L cube by 3 EI. You have this goes off 16, L cube goes off. VB is nothing but 5P. Am I right? Is it 5P by,
Yeah, 5 by 16.
yeah,
16.
yeah, 5P by 16. Correct. Yes, this is going to be 5, yeah, 5P by 16. 5P by 16. So this is the standard. Now, once we know VB, right? Once we know VB, now what is unknown? So let me draw the beam again. We have this beam, the cantilever beam, the propped cantilever beam. This is P. This is something which we just right now we have found it. This is going to be 5P by 16. So now you just do the, you can have the equilibrium equations into the coming to the picture. So you what is this is A, this is B. So VA plus VB should be equal to P. So VA is going to be P minus 5P by 16, that is 11P by 16. So this is going to be 11P by 16. What about the moment? So moments are directly, you sigma MA equal to 0. That implies 5P by 16 times L minus P times L by 2. Yeah, this you can find out. So this is 5PL by 16 minus PL by 2. This is 16. 5PL minus 8. 3PL. Yeah, 8, right? Yeah, 3PL by 16. So we have 3PL by 16. In which direction? So that is important. So this is going to be in this direction. 3PL by 16. All right. So this is how we usually work on. So I hope now it is clear how we are making use of the compatibility equations here. So the compatibility is again nothing but we try to break the indeterminate beam into two determinate structures, and we'll find the common point there. We'll try to find out the displacement is there, and then we'll try to equate again displacement. Right now we are using the same problem can be solved in another means also, right? So for example, in this what we have chose the vertical reaction here, the vertical reaction as a redundant force, right? This can also be solved as let us say I have a cantilever beam, prop cantilever, some load P. This I can also break down as uh, sorry, a simply supported beam, okay, a simply supported beam with moment M. Okay, I can do the same thing here too. So in this, what will be the compatibility equation? In this, the compatibility is something like this. So this is P. The compatibility is this is A, B, A, B. So here we have rotation theta at A, right? Theta A, and here we also have rotation theta. Let me call it as theta A, theta A prime. I'll call this as theta A double prime. Okay, this is not the differentiation. This is just just to name it the rotation at support A. So we have theta A double prime, theta A prime. What is the compatibility at for a cantilever or the fixed support? So the compatibility is that theta A prime plus theta A double prime should be zero. We can also solve in this way, in this method again, rather than just taking the vertical force as a redundant force. We can also use this kind of a equilibrium equation to find out sorry, compatibility equation to find out uh, so in this we'll find M, we'll get the compatibility equation in terms of M. So anyways, I think this is just an introduction, like how we are making use of the compatibility equations to find out the indeterminate structures. Let me solve one more question on the same beam members, and after this maybe we can solve one question on the frame members. I think that will give you some. I think that will give us uh, some preparation to actually work on the coming sessions. So I hope there is no question. There is no doubt in the first question. It is clear. Is it clear?
No, sir.
Yeah.
Yeah,
Thank you.
yeah, yeah.
Okay. Thank you. So second problem. Again, this is one of the standard problem. I think you all know the solution for this, but let us again, we'll just try to formulate or try to uh, find out the support reactions again from the basics. Okay. So this is a fixed beam. We usually call it as a fixed beam. Okay. So this is a fixed beam with UDL. This is UDL, and I'll call it as W. So that is how we usually denote A and B support. Okay. So we have A and B. We have W. So how do we break this down? So from this we also formulate the flexibility matrix. Okay, what is the flexibility matrix? So we'll try to. I'm not using any numericals in this. Let us solve for W and L only. So I'm not using any numericals, so that we can kind of we can make a generic we can make a generic flexible, we can formulate a generic flexibility matrix from this. So this is W, this is L. Yeah, first thing, let us what whether is it determinate or indeterminate. So it is again, we have two M, we have MB, MA, VA, and VB. So we have four equations, four unknowns, four unknowns. And how many equations do we have? We have not three, because we don't have any inclined forces, right? We have two equilibrium equations. Okay, like I said, if you have some inclined forces, let us say it is P, then you will also have let us say horizontal at A and also horizontal at B. So right now we are not dealing with such kind of questions. So let me just let me deal with only the gravity loads, right? The gravity loads. So the gravity loads, we have only the vertical loads here. This is P or whatever it is, just for the, yeah. So we have two equilibrium equations. We have four unknowns, 4 minus 2, that is the static degree of static indeterminacy is 2. So two redundant forces we have. So we need to have two compatibility conditions. Okay. So what are those? Let us again formulate that. We'll just break down this. So the first step is breaking down the indeterminate structure to determinate structures. Okay. So how can I do it? So in this, what I'll try to choose is again the cantilever, because it is easy to solve. Cantilever beam plus, let me take that's what, if it is a cantilever, now my two redundant forces are going to be one vertical force VB, one that is at B. Let me draw it small because I don't have space here. I'll just draw it as small. Please assume this has the same beam. So we have MB here, MB. So I have VB, I have MB. So what will be the what will be my compatibility equations? So in this again, you have I'll call this as delta B. Okay, this is delta B, and I also have theta B, theta B. So delta B, because of this, and this, from this time onwards, let me call it as delta B dash, and because of a moment also we'll have delta, right? So this is delta B double dash. I'm just calling it as delta B double dash. So delta B plus delta B dash plus delta B double dash is equal to 0. This is compatibility equation number 1. And also we'll have theta B plus, we have, let me draw it some, yeah, this is theta B dash, and this is theta B double dash. Yeah, theta B plus theta B dash plus theta B double dash is equal to 0. This is my second compatibility equation. So in addition, we have equilibrium equation, that is force, sorry, Fy. This is force Fy, that is equal to 0, and also we have M, that is equal to 0. This is third equation. This is fourth equation. Four equations, four unknowns. We can solve it. Okay. So let me start solving the question. So first is the main beam. So let me call this as beam B. This is 1, this is 2, this is 3. Okay. So now 1, we have a cantilever beam with the UDL. This is okay. Yeah, this is UDL cantilever beam. Um, A and B. Okay. Now this is delta B, and this is theta B. First, let me find out delta B. How do you, what is delta B? So we have just a second. I'll just close my windows. Just a minute. Yeah. So we have delta B. So how do you find? So let us. I think now, right now, we are very uh, we are very accustomed to using bending moment diagram. So let us find delta B. Delta B is how much? So first, let me solve for delta B. So you have W. What is the bending moment here? WL WL square by 2 here, and this is my bending moment diagram, right? So WL square by 2L. So what is my
delta b
delta b is nothing but the
moment of
moment
the
of
area,
the
Bray
area,
moment
Bray
area,
moment area,
about the point
about
of
the point
interest.
of interest. So this is my b
This is
and
my
this is
a.
my a.
Okay.
Okay,
So
so
delta b
delta
is
b
nothing
is
but
nothing but
what is my
what is my
what is the area
what
of
is the
this?
area
This
of
is
this? This
one
is
third
one
of
third of
w l square
WL
by
square
2
by 2
times L.
times L.
Okay.
Okay,
Times
times
this is 3
this
by
is 3
4.
by 4.
So these things
So these
actually
things actually you can I hope you know about the centroids for this kind of a problem. So this is 3/4.
so
So you'll be getting
w l
W
power
L
4
power
by
4 by
8
8 EI. So I just missed. I always
this is
miss
EI.
writing EI.
This is EI.
This is EI.
So
So
again, how do
again,
we know
how do we know whether like I just want to again just
emphasize
emphasize
why are we
why are we
taking
taking the bending moment diagram
in this
in
fashion
this fashion
but not in
but
this
not in
fashion?
this fashion?
Okay.
Okay,
I'll just
I'll
explain.
just maybe I think you know the answer, but let me again explain it so that it will reconfirm your
Way of
way of
understanding.
understanding.
So
So
as we know
we know that
what is shear
what is
force?
shear
Shear
force?
force
Shear
is
force is
nothing
nothing
but
but
the
the
first
first derivative of the bending moment diagram, right?
so
So
it's very
it's
easy
very
to
easy to
understand how to
understand
draw
how
a
to
bending
draw
moment
a bending
diagram.
moment
So
diagram. So
you know
you
that
know
at this
that at
point
this
B,
point
you
B,
can see
you
the
can see the
point B.
point B.
This
This
point,
point,
there's no
there's
shear
no
force
shear
present,
force
right?
present, right? The
Point
point
B,
B we have
zero.
zero. The shear force is zero. That means
dm by
dm by
dx should be
dx should be
0.
zero.
If
So if
dm by
dm by
dx should
dx
be
should be
0,
zero,
that means it
that
should
means
be
it should be
tangential to the
tangential to the
horizontal
horizontal
axis.
axis, right?
In this
In
case,
this
you can't
case, you
see.
can't see. This
In
is
this
in
case,
this case you,
there is
that
some
there is
tangent
some tangent
present.
present. That
There is
means
some
there is
shear
some
force
shear
acting.
force acting.
So this is
So this
wrong.
is wrong.
So
So in the second case, you can see
second case,
second case you are actually
after it,
after it you're
making
making
it
it
as a
as a
tangent.
tangent here.
So in
So
this
in this
case,
case,
at that
at
point,
that
dm
point
by
dm
dx
by
is
dx
0,
is 0,
which actually
which actually
represents the shear
represents the
force
shear
at
force
that
at
point.
that point as 0.
Uh,
uh,
otherwise,
Otherwise you can also plot,
you can
you
make
can
some
make
plots
some
here,
plots here,
and then you
and
can
then you
find
can
out
find out
this
this
plot is
plot
going
is
to
going to
be
be
a
a
uh,
um,
uh,
uh,
a
a
parabolic
parabolic this is a parabolic equation,
and also
and
you
also
can
you can
find
find
out
out
the bending
the
moment
bending
diagram,
moment
and
diagram,
you'll
and
find out
you'll
the
find out
curve
the
to be
curve to be
coming out
coming out
something like
something
this.
like this.
Anyways,
Anyways,
so we
so
have
we have
delta b,
delta b
that is
that
equal
is
to
equal to
w
W L
l power
L
4
power
by
4 by
80 I,
80 I.
and
And
also
also,
what
what
about
about
theta
theta
b?
b? Yeah, theta b is also
Important in this
important
case.
in
So
this case.
theta
So
b is
theta b
nothing
is
but
nothing but
the
the
area
area
direct,
direct. So
the
it's
area
the
of the
area
bending
of the
moment
bending moment
diagram.
diagram.
So that is
So that
nothing
is
but
nothing
1
but
by
1 by
3
3
w
WL
square
square
by
by
2
2 times
L
L
by
by EI EI.
w l cube
WL po
w
sorry
l cube
WL
by
cube by
6 EI.
6 EI.
Okay, this
Okay,
is my
this
theta
is my
b.
theta B.
Okay,
Okay,
so in this
so
case
in this
my
case,
delta
my
b is
delta
in
B is in
downward
downward
direction,
direction,
and
and
how
how
is
is
theta?
my
Theta
theta?
is
Theta is
in
in
clockwise.
clockwise. This is clockwise.
Fine.
Fine.
So let
So
me
let
take
me
up the
take up
second
the
one,
second
that is
one, that is
beam 2.
beam 2.
Beam 2,
Beam 2,
we have
you have
similar kind of
similar
thing.
kind of thing. What is beam 2? And
Beam 2 is
beam
with
2 is with
unknown force
unknown force
VB.
VB.
Unknown force
Unknown
VB.
force VB.
All right.
All right.
So
So VB,
VB.
VB.
This is
This
A.
is A.
This
This
is
is
B.
B.
I'm not
So
going
I'm
to
not going to
derive
derive
again
again
what
what
is
is
delta
delta
B
B
dash.
dash.
We have
We
already
have
had
already
this.
had this.
VB L
VB
cube
L
by
cube by
3 EI.
3 EI.
Okay.
Okay.
And what is
And
theta
what is
B
theta
dash?
B
Theta B
dash?
is
Theta
nothing
B is
but
nothing but
VB
VB
L square
L
by
square by
2 EI.
2EI.
Okay.
Okay,
So in this
so in
case,
this case this is going to be this is
upwards,
upwards.
because
Okay, because
the beam is
the
actually going
beam is actually going upwards like this.
this is delta
This
B
is
dash,
delta B dash,
and also
and also
this is the slope,
this is the slope which is clockwise, sorry,
anti-clockwise.
anti-clockwise.
What about
What about 3?
beam 3?
Beam 3.
Beam 3
Beam 3 is again the cantilever with, I think, with the moment MB.
A
A
moment
moment
MB.
MB.
So you are
So you are
rotating it
actually
in
rotating it in
clockwise
clockwise
direction.
direction, so the beam is going to bend upwards.
Okay,
Okay,
upwards.
sagging.
So it is going to bend
So this is
upwards.
going to bend
And
upwards. So we'll have
delta B
delta
double
B
dash,
double dash,
and also
and also
anti-clockwise.
anti-clockwise delta B double dash.
In this
I think this we didn't solve. Let me solve it here.
so we
So we
Now
have
MB,
MB. So MB, there is no shear force.
again this is
Again, this is
frequently asked
frequently asked in most of the
exams or
exams or
something.
something. They'll just ask in a cantilever
If you
beam, if
apply
you apply
momentum,
momentum, what is the shear force? So there will not be any shear force. It's only
there's only
there's
bending
only
moment.
bending
So
moment.
this
So
is
this is
also a
also
case
a
of
case of
no shear
no
force
shear
and
force
bending
and
moment.
bending moment. What is it called?
Pure bending.
Pure bending, right?
Okay.
Yeah.
So
So
this is
this is
MB.
MB.
Okay.
Okay.
This is
This
also
is also
MB.
MB.
Again,
Again,
I want to
I
find
want to
E by
find
EI.
by EI and by EI. So
This is my
this is
area
my
of
area of
bending moment
bending
diagram
moment diagram
or the
or
curvature
the
diagram
curvature
and by
diagram
EI
and by
diagram.
EI diagram.
So
So
delta B
delta
double
B
dash
double dash is going to be
half.
half.
Sorry, there's no
Sorry,
half.
there's no half here.
Rectangle.
It's rectangle, right? Oops. Okay. Yeah.
So this is
So
nothing
this
but
is nothing but
MB
MB
times
times
MB by
MB by EI
EI into
into
L
L
times L by
times
2.
L by 2.
So this is
So
quite
this is quite
straightforward.
straightforward.
MB L
MB
square
L
by
square by
2EI.
2EI.
This is going to
This
be
is going to be
upwards.
upwards.
What about
What about
theta b double
theta
dash?
B double dash?
So theta b
So
double
theta
dash
B
is
double dash
directly
is
the
directly the bending
area
moment
of bending
area
moment
of bending
diagram.
moment diagram.
MBL
MBL into EI, that is what it is. So it is
anti-clockwise.
anti-clockwise.
Okay.
Okay.
Now we have
So now
found
we have found out delta B dash, delta B double dash, theta B double dash,
and
and
also
also
theta b and
theta
delta
B
b.
and delta B.
Okay. So
Okay.
what is
So
my
what is my
compatibility
compatibility equations?
equation?
These are my compatibility equations.
These are my
These are my
compatibility
compatibility
equations.
equations.
I'll try
I'll
to
try to
apply these
apply these
compatibility
compatibility
equations
equations
in
in
my
my
to solve the
to
for
solve for.
and what
And
are we
what are
solving
we
for?
solving for? We are solving for
VB and
VB and
MB.
MB.
Okay.
Okay.
So
So
let me write
let me
down
write
the
down the
same
same
equations.
thing as an equations here.
So what I
So
can
what I
do
can
is
do is
we
we
have
have
MB.
MB.
What is
What is
MB?
MB?
MB is
Delta B is
WL power
WL power
4.
4.
Yes.
Yes. W.
W.
Let me write it again. Okay, fine.
By
By
4
4
EI.
EI.
Okay.
Okay.
This is
This is
downwards.
downwards,
Let me
right?
take
Let me
downwards
take
as
downwards as
negative.
negative.
Plus upwards
Plus
I'll take it
upwards,
as
I'll take it
positive.
as positive.
Other
Other,
you can take
you can take
uh,
uh,
you can
you
take the
can
sign
take the sign
conventions,
conventions,
but
but as this is an
algebraic
algebraic
sum.
sum,
I am
I am
assuming
assuming
downwards
downwards
as
as negative
negative
and
and
upwards
upwards
as
as positive.
positive.
Okay.
Okay.
So we
So we
have
have
VB
VB
L
L
cube
cube by
L cube
L
by
cube by
3
3EI
plus what is the
plus
other
what
one?
is the other one?
MB L
MB
square
L
by
square by
2
2EI.
MB
MB L
by
square by
2 EI.
2EI.
That should be equal to
That should
0.
be equal to 0. This is one equation number one.
So what
And
is the next
what is
one?
the next one?
So next
So
one
next one,
yeah, this is
yeah, this is clockwise, right? So
clockwise. I'll
clockwise,
assume
I'll
it as
assume it as,
let me assume it
let me
as
assume it as
negative.
negative here.
So
So
minus
minus
W L
W
cube
L
by
cube by
6
6, sorry, 6 EI.
6
6 EI. It is
EI.
6 EI, right?
Yes, it is
Yeah,
W
it is
L
W L
cube
cube by 6 EI
plus
plus
VB L
VB
square
L
by
square by
2
2
EI
EI
plus
plus
MB L
MBL
by
by
2 EI that is equal to
EI,
0.
that is equal to
So we
0.
have
So we have
VB,
two
VB
unknowns,
and MB are
VB and MB
unknowns.
are unknowns. We have two equations. It is easy to solve.
We'll just
Let me
formulate
just
them.
formulate the.
You can write this
You can write this again.
you can
You
actually
can
write
actually
it
write it in
in
matrix
matrix
form,
form.
right?
So how
So
can you write
how
it?
can you write it? So you can just simply
Write something like
write
this.
something like this:
L
L
cube by
cube by
3
three EI,
L square
L
by
square by
2
two EI,
L square by
L square
2
by
EI
two EI,
L by
L by EI.
I'll get
I'll get
a
a
column matrix which
column
is
matrix which is
VB
VB
and
and
MB.
MB,
That is going to
that is
be
going to be equal to WL power 4
by 8
by 8 EI,
WL cube by
WL
6
cube by 6
EI.
EI.
Okay.
Okay.
Now
Now
this is nothing
this
but
is nothing but
flexibility matrix
flexibility matrix
or flexibility
or
term.
flexibility term. Let me call it as matrix because we have written it,
And this is nothing
and
but
this is nothing but
force matrix.
force matrix.
This is nothing but
This is nothing but
displacement matrix.
displacement matrix.
Okay.
Okay.
This is
So you can see this is again symmetric. Okay.
So
So next, yeah, you need to just solve for this.
VB and MB
VB
are
and MB
unknown,
are
so you need
unknown,
to take
so you
inverse
need
of
to
this
take inverse
matrix.
of this matrix.
Not
Sorry,
not here.
not here.
You just
You just transfer matrix to this side and you take inverse of it, and you multiply with WL power 4 by 8EI,
and WL
and
cube by
WL cube by 8EI,
and then you can
and then you
solve
can
for it.
solve. So once you solve for it, you'll get VB
And
and MB,
that is going
that
to
is
be
going to be equal to
WL
WL, sorry,
WL by
WL by
2,
2,
and this is
and
going
this
to
is
be
going to be WL square by 12.
perfect.
Okay.
So
So
this is
this
how
is how we
try
try
to
to
formulate
formulate.
uh,
Uh,
this is how we
this is
try
how
to
we try to
formulate
formulate
the
the
matrix, right?
matrix, right? So this is how we are trying to find out.
Uh,
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 again,
Again, let
for
me, for
example,
example, I can use the same equation.
I can
I can use the same equation.
you need to
You need to
understand these
understand these
displacement terms are
displacement terms
because
are
of
because of
the
the
uh,
uh, because of the UDL present on the cantilever beam, right? UDL present on this cantilever beam. So this is actually these displacement. This matrix which we have found out is the displacement due to the
um,
um, these
these
are
are
because of
the
the
UDL.
UDL.
Uh,
Uh,
for
for
example, if we
example,
have
if we have
maybe a
maybe a
point load,
point load, okay, let us say if we have a point load
like we
like
have
we
done,
have done, let us say this is my
matrix.
matrix, we have this something like that, we have a point load P
Acting at
acting
the
at the
midspan.
midspan.
So
So if
in
in
this
this
case,
case,
what
what
again?
again,
What
what
are
are
we
we
going to
going to
do?
do?
So
So we
the
the
matrix,
matrix, this part, the
this
left
part will
side
be the
part will be
same.
the same,
This part
this
will be
part
the
will be the
same.
same,
But
but this we, you need to just substitute, you need to find out this is
delta B
delta B
and this is
and this
theta
is
B.
theta B.
So
So for the
corresponding
corresponding
load
the
pattern,
load pattern, or
the load
the load
acting,
acting,
you
you
need
need
to
to
find
just
out
find out
for the
for
same
the same
cantilever.
cantilever,
You need to
you
just
need to
find
just
out
find out
theta B,
theta B
delta B.
delta B.
So
So
again, you have
again,
the
you have the
flexibility
flexibility
matrix
matrix F
and the
and
unknowns
the unknowns VB MB,
that is
that
nothing
is
but
nothing but
delta B
delta B
in
in
this
this
case and
case
theta
and
B in
theta
this
B in
case.
this case. Okay.
So
So
this
this
you need to
you
just
need to
change
just
and
change,
the
and the
flexibility
flexibility
matrix
matrix
remains the
remains the
same.
same.
VB and MB
VB
can
and
be
MB
found
can be
directly.
found directly.
So
So
this
this
is
is
how
how
we find
we
out
find out
the
the
flexibility.
flexibility.
We find
We
out the
find out
unknown
the unknown
reactions
reactions
using the
using the
compatibility
compatibility
equations.
equations.
In this
In this,
actually,
actually,
what
what
we
we
are
are
trying
trying
to
to
do
do
is
is
we are trying to apply
apply
force.
force.
We are trying to
We are trying to
apply
apply
unknown
unknown
force,
force,
and we are
and we
trying
are
to
trying to
find out the
find out the
displacements.
displacements, right? So that is the reason why it is called
Force
as the force
matrix
matrix or the
and
displacement.
it's
Sorry,
called
it's
as the
called as the
force
force
matrix
matrix
or the
or the
flexibility
flexibility
matrix.
matrix.
So we are
So we
trying
are
to
trying to
apply some
apply some
force,
force,
and then we are
and then we
finding
are
out the
finding out the
displacements.
displacements.
That is the
That is
major
the major
difference
difference
between
between
flexibility
flexibility
matrix
matrix and
and
the
the
stiffness
stiffness
matrix.
matrix.
For
For
the
the stiffness
stiffness
matrix,
matrix,
we'll
we'll
apply the
apply the
displacement and
displacement
we'll
and we'll
find out
find
the
out the
force.
force.
Okay.
Okay.
So
So
again,
again,
the
the
definition of
definition
the
of the
flexibility
flexibility
is
is nothing but the flexibility is
displacement
displacement
per
per
unit
unit
force.
force.
Okay.
Okay.
You can see
If you
here,
can see here, this is nothing but the force.
flexibility is
Flexibility is
nothing
nothing
but
but
delta
delta
displacement
displacement
by
per
per
the
unit
unit
force.
force.
Okay.
Okay. If you apply, that is what we are doing here. You can see
You are
you are
applying
applying
VB
VB
and
and
you
you
are
are finding
finding
out
out
delta B
theta
and
theta B.
theta B.
You are
You are
applying
applying
MB
MB.
is
MB
also
is also a
a
force,
force,
right? So
right?
MB,
And you are
and you are
finding out
finding out
theta B
theta
and
B
delta
and
B.
delta B.
Similarly,
Similarly, you
you have
have
an
an
external
external
load,
load, external force
W,
W,
and
and
you
you
are
are
finding
finding
out
out
delta
delta
B
B
and
and theta
theta B.
B.
So,
So,
what
what
happens if,
happens
for
if, for
example, the
example, the
same
same
question has
question
to be
has to be
solved?
solved for what if
Support is
support is
settling down?
settling down?
Okay,
Okay, let me solve the same question.
we have the
We have
same
the same
W,
W, the
force
force
here.
here.
Uh,
Uh,
let
let
I'll
I'll
just say
just
how to
say how
solve
to
the question.
solve the question. That's it. But
Uh,
I'll
let us
let
have
us have. Okay, let me take a new page.
the same
The same
question.
question. This is again a
Same
same
cantilever
cantilever
beam.
beam. The
The
cantilever
cantilever
beam.
beam gets settling.
Yes.
So that equations what you have arrived at initially, cannot it be simplified further before in writing the matrix? Because L,
Yeah,
L,
Yeah, L
L
square.
and
Yes,
all can be
yes,
cancelled.
yes. Yes, yes. See, the reason why I have actually showed in this way is like, for example, when you are using it for something else, like for example, if you have P here, right? So if you have P here, this will be remaining the same. So this L cube by 3, L square by 2, L square by 2, this will be the same, because this does not have to do, these terms does not have to do with what is the load coming on it, right? It is only, it has to do only with VB and MB, what kind of VB you are giving and what kind of MB you are giving. So if you have a point load P, then what happens, then your this term will be in terms of L cube. This will be something like L cube. This is nothing but PL cube by 3 EI, and here it is PL square by 6 EI. You are able to understand?
Yeah. Hmm.
Yeah. So that is the reason why I actually I wanted to keep this as a constant, so that you can use this generically in any kinds of equation. For example, let me if this is P, otherwise you also have the same question, but let me load it halfway through, only halfway. So even in this case, you can use the same flexibility matrix. I think I have messed it up here. Like you can, I hope you can see it clearly. Yeah, this flexibility matrix, you can use the same flexibility matrix, but only thing you need to change is these things. So for these things will be actually the displacements because of this load, delta B and theta B. So in this it will that's why actually I did not further simplify this one. Otherwise, like you said, yes, we can further simplify, and we can directly find out VB and ML.
Okay.
Yeah. uh, Fine. Let us solve one question on. I'll just solve one question on how, if what happens if the support settles. Okay. The same question, we have the same question here. So we have the same fixed beam with UDL. Oh, UDL W. This is A. This is B. So what is yeah, the W is not W is given as 10 kilonewton per meter, and the length of the beam is 12 meters. This is problem 3. Length of the beam is 12 meters. Now what he is trying to tell is, the question in the question, support support B settles by 5 mm. Okay, so 5 mm is the support is going to settle by 5 mm. So, and also E, it is given as 200 GPa. Again, this is steel beam. I, you can take it as 300 into 10 to the power 6 mm to the power 4. Okay. So if the support B is going to settle, right, so what happens to our compatibility equations in this? So for example, in this, what we are trying to say, there is no support settlement, and then we have formulated by saying that delta B plus delta B dash plus delta B double dash is going to be 0. But in this case, we need to understand that delta B plus delta B dash plus delta B double dash. Again, we need to be very careful on how we are actually defining our vertical and I mean uh, the sign conventions, right? So delta B plus delta B dash plus delta B double dash. In this case, what I'm trying to do is I'm trying to take all the delta B positive, I mean all the deflections positive in downwards directions. Okay, so otherwise, like the previous ones, let us take it positive in upward directions, but then minus 5 equal to 0, because it is settling down, right? It can't settle up, so it is settling down. That means it is coming down, maybe due to, maybe there is some issues with the soil, underlying soil, or maybe the beam itself has been has gone down, which is carrying this support B. Whatever the reason may be, the settle the B has came come down. So we need to be again careful by when you are defining delta B here, because this is in mm, right? You have to calculate all these things in terms of mm. Okay, so that care has to be taken. So I'll just mention the equations, like what are the equations, how are we going to solve this kind of an equation. So for this I'll take the same thing. So we have the same L cube by 3 EI, L square by 2 EI, L square by 2 EI, and L by EI. Let me just simply write L cube by 3 EI, L square by 2 EI, L square by 2 EI, and L by EI. This times VB and MB. Now we need to be careful. So in this, what we are assuming is delta B is yeah, this is positive downward, so delta B is upward, so this minus. So in this, what happens is that we have W L power 4 by 8 EI, okay, plus 5. If you remember, delta B we have taken downwards here, and delta B dash is upwards, delta B double dash is upwards, and 5, which is actually downwards. So this should be W L power 4 by 8 EI plus 5. Okay, and also we have in this there is no rotation in this case, right? In this case, there is no rotation. I mean, the rotation at the fixed support is always 0. So it is again similar to the previous one, that is W L cube by 6 EI. W L cube by 6 EI. So I think if you solve this, you have W, you have L, and you also have EI, and also you have yeah, you need to solve all this in terms of mm. Okay, all these things in terms of mm. So when once you solve this, you are going to get VB and uh, what is VB? VB, you are going to get 57 point. VB is going to be 57.92 kilonewtons, and MB is going to be 107.5 kilonewton meter. Okay, we'll just compare it with without support settlement. What happens if if there is no support settlement? If there is no support settlement, right? Then what is going to happen? So if there is no support settlement, VB. So this is with support. I'll just yeah. So I'll just outline it. So this is with support settlement, and without support settlement, this is W L by 2, and MB is W L square by 12. Okay, so WL by 2 comes about 12 into 10. This is 60 kilonewton. Okay, and this is going to be 10, 12, 12 by 12. So this is 120. So you can see there is a quite a reduction of the shear force in VB, and also the bending moment at MB has been decreased. Uh, what happens to VA? So for VA, this has to actually counter. The VA has VA, there is extra bending moment generated there. So if you check for the VA, again without support settlements, this is 120. 10, 12, 12 by 12. Yeah, this is 120. So this is 120 kilonewton meter. So in this case, VA is going to be 60. How much to 120? So this has to be 62.1 kilonewtons, and MB is going to be you can find out. Let me just find out MB. MB is going to be 57.92 times 12 minus 10 times 12 times 6. We have also 107.5. So this is acting upwards. Forces are acting up, and MB is going to be this in this direction. So this and this has to be in the same direction of in the same direction of that. This is going to be my MA. So 107. Let me solve this. I didn't solve it. I'll just. Uh, what is this going to be? 107.7.5. 107.5 plus 10 times 12 times 6 minus 57.92 times 12. So this is going to be 132. 132. Yeah, 132. So 132.46 kilonewton meter. Okay, this is 132.46 kilonewton meter. So with this we can make some conclusions. For example, if a support is settling, that support, it is kind of releasing its the support, the reactions, right? It is yielding down, right? So if it is yielding, that means the support is not going to take that much of force, so it releases some reaction here. Initially without any support settlement it has to be 60, but right now it is 57.92. MB has to be 120, but it has actually become 107.5. um, at the same time, uh, uh, MA, what is it? Yeah, MA has to be 120, but it is actually right now it is taking more bending moment, that is 132.46. And the shear force before it is around 60 kilonewtons, but now it is about 62.1 kilonewtons. So again, the support settlements has to be actually taken into account when we are actually designing for the structure. So support settlements induces the bending moments, right? It induces it increases the bending moment. So that is what we have learned from this example. So we can see that as the supports are settling, at that support which is settling, it is actually releasing some of its forces, but the other end of the supports has to actually balance those forces by actually taking the extra forces or the extra bending moments from that. So I hope this problem is clear. Shall we move to the frame problem?
Yeah, yes.
Yeah, yeah. So let us just go to the next question. That is, let us discuss one frame problem, and we can yeah. So we have a so for the frame problems, usually I prefer using the energy methods. So I hope that is fine, because we already solved a lot of problems, a lot of, I think not too many, but I think we have used some 4 or 5 problems we have solved using the energy methods, right? So we'll use the same energy methods to find to solve these frame problems. So let me have the question. So yeah, we have this question. We have a frame. Yeah. Okay, let me take this question. We have this is problem 4. We have a frame, the roller support. Okay, this is 8 kilonewton per meter. Oops. This is 8 kilonewton per meter, and we also have a horizontal force on this member. This is, yeah, anyways, I have drawn it. Please assume this as UDL. This is 4 kilonewton per meter. Okay, not to the scale, but Please assume this as 8 and this is 4 kilonewton per meter. And the distance, this is A, B, this is C. So we have, this is 9 meters and this is 6 meters. Okay, so now solve for the support reaction. So that is the question here. So let me again use the same concepts which we used so far. So in this question, what was given? The EI is constant in all the beams. EI is constant. Okay. So how do we solve for this? So let us first discuss about the static indeterminacy. So we have, let me draw the beam again. We have the beam something like this. So we can have bending moment M here. We can have vertical force VA, and also we can have horizontal force HA. We can have a only vertical force VB. Sorry, this is VC. Okay. So a number of unknowns. Number of unknowns are one, two, three, four. Four unknowns. Number of equations or the equilibrium. It's better we call it as equilibrium equations. We have three. Those are Fx equal to 0, Fy equal to 0, and sigma m equal to 0. So static indeterminacy is 4 minus 3, that is 1. Okay, ds is equal to 4 minus 3, that is 1. So 1 is the redundant force. So again, I'm again comfortable with using the cantilever beam. Otherwise you can also try with the simply supported, and then yeah, one point I mentioned, actually I forgot to mention. For if the in the previous question, right, in the previous question, let me have, we have something like this. And okay, this is not a valid one. Let me take another example. For example, if you have, this is again not based on this question. Okay, for example, if you have something like this. Okay, you have two simply supported beams, and there is one force, inclined force acting here. Okay, if it is not inclined, then if it is simply P, if it is vertical force, then it is easy to, there's nothing to analyze this. It is again a there's no issues with solving the problem, because it is again similar to the simply supported beam. But if you have something like this, right, if you have an inclined force coming, right, you have to assume, or maybe let us for the let us make it a little more complicated. You have a roller support here and also a roller support here. Okay, you have two roller supports, a continuous beam kind of a thing, and you have a vertical load have a vertical load you have a vertical load acting here. Okay, this can be, again, you can use the compatibility equations, this one, and you have a roller support and roller support here. Okay, so this you can actually break down into this one. There are too many options. You can actually make all the roller supports, but this is actually not a stable stable configuration. Okay, so better you actually avoid using unstable configurations, or which are not the stable configurations. Okay, so this can be solved using this kind of, you can remove this and you can just place one unknown VB or something like that. And also, otherwise, you can also do, you can make this, but it will be like a overhang beam with end VC. Okay, so this is just, I just want to mention, this is an additional point. So let us solve the main question. Let us solve the main question. So the main question is the frame member with, now right now we have a static indeterminacy as 1. Let me remove the support C, and I'll apply a load, vertical load VC there. Okay. So I want, I the same question. I will, with this I'll break down as the cantilever support plus, okay, all, always I'm not having space for that, so let me write down here. Sorry. Yeah. So yeah, in this this is what did we call this? C, A, B, and C. This is one. This is beam one. I'll call it as, sorry, frame one, and this is frame two. Frame two. So here I'll apply VC as my unknown force, and then I'll find out the compatibility equation. So what is going, like what is my compatibility in this compatibility conditions in this case? So my compatibility conditions are going to be, this is delta C, this is again delta dash C. So delta C, the vertical reaction here, sorry, vertical displacement here, delta C plus delta C dash is going to be 0. So in this, delta C dash will be in terms of VC, and delta C is again the known displacement. So delta VC can be found using the same equation. So if again this is an frame member, so it is very easy for us to find out, use the virtual work method or the unit load method. Okay, so this is frame 1, frame 2. So let me just solve for frame 1. We'll solve delta. So now I'm going to take frame 1, frame 1. So what is frame 1 going to be? Frame 1 is with external load without sorry, it is an indeterminate, it is a determinate frame with external loads. So the external loads are something like this, and you also have, this is 8 kilonewton per meter, and this is 4 kilonewton per meter. This is going to be C. Huh. Now this is when we are using the unit load method. What are we discussing before? And also you might have again, you just try to remember what we are doing before. We are trying to apply a unit load uh, in the direction of, in the direction or at the place or at the point of interest in that direction, and we are actually integrating to find out the displacement there, right? So what happens is that I'll have a real beam or the real frame, and I'll apply, how do I apply? So let me apply in this direction, unit load 1 kilonewton in this direction. So let me solve for this. uh, yeah, let's solve the support reactions here first. Let me solve the support reactions. So the support reactions are going to be 8. This is 8. So 8 times 12, 9, 72, right? 72, 4, 6, 24. This is 24 and 32. So 74, 72 times 4.5. Okay. Mm, again, plus 24 times 3. This is going to be 396 kilonewton meter. 7 to 80. So yeah, this is going to be 396. So this is going to be in this direction, 396 kilonewton meter. Now what about the vertical reaction? The vertical reaction entirely is taken by the support A. So this is 72. This is 72 kilonewtons. Horizontal reaction here it is again 7, sorry, 24 kilonewtons. Okay, now we have solved for the support reactions. We'll do the same thing for the unit with the unit load. So you have 1 kilonewton acting here, so you directly have 1 kilonewton which is down, which is downwards at support A. So 1 kilonewtons which is creating a clockwise, you will develop anti-clockwise moment that is developed by 1 kilonewton the unit load, you will have an anti-clockwise moment of 9 kilonewton meter developed at support A. Okay, this is my actual beam with the real loads, and the actual frame with actual beam with actual frame with real loads, and actual frame with virtual load of 1 kilonewton meter. So if you remember what we are discussing about uh, A, B, and C. So we need to find out capital M and small m, right? So 1 into delta C is nothing but the summation of capital M small m by EI dx. Okay, this is the strain. This is my the elongations in the member. So for BC, you can so let me again, we follow the same procedure what we are doing before. So this is span, length, uh, capital M, small m, sorry, capital M, small m, and this is capital M, small m by EI dx. Okay, so the span, let me name it as AB. For AB span, what is the length? 9 meters is the length, and the capital M is going to be uh, so this is at distance x. This is going to be minus 396 hogging moment, mm, plus 72x minus 8 into x by 2, that is 4x square. Okay, this is my capital M. What about my small m? My small m is going to be, this is sagging 9, uh, sagging moment 9 minus x. Okay, so you take at x 9, which is positive, minus 1 times x, which is 9 minus x. So this is going to be 9 minus x, and this will be so on and so forth. So what about BC? Length is 6. What is my capital M going to be? Capital M is going to be 4 times x by 2, that is 2x square. Okay, but my small m is 0 because there is no bending moment developed here. So this is going to be 0. So obviously we'll have delta C is again is defined by the only the member AB. All right, AB 9 minus x, 72x minus 4x square minus 396 divided by EI dx, ranging from 0 to 9. This is found out to be 9477 by EI. 9477 by EI minus. What does the minus sign mean? So minus sign means that we have assumed the unit load upwards as positive, right? But the displacements are going to be downwards. So the displacements are going to be downwards. That means when you're loading this kind in this scenario, the beam is going to bend something like this. So this is the beam is going to have a displacement somewhere in this. So this is delta C. Sorry, yeah, displacement C. So delta C is going to be 9477 by EI. Now the half of the problem is done. What is the what is the next process? The next part is frame B. This is frame A. This is frame 1. Let's go for frame 2. What is my frame 2? Frame 2 is nothing but I'll apply a redundant force VC. This is VC. Yeah, apply a redundant force VC and find out delta C dash. So delta C dash is how much? Again, for this again we formulate the unit. We'll use the unit load method. The same unit load I'll be applying the load 1 kilonewton. So I think we can use the same diagram, 9 kilonewton meter and 1 kilonewton meter. 1 kilonewton and 9 kilonewton meter. So this is going to be again pretty straightforward. This is VC. This is going to be VC, and VC times 9, and you again have 9 times VC.
Okay.
Okay.
So
So if this is going to be 9 times VC, will what is my delta C dash? Delta C dash is going to be again, in this we don't have any bending moment in A, B, C, A, B, C. There is no bending moment in BC member, right? So I'm not going to consider my BC member directly. Now I'm going to write delta C dash is going to be integral 0 to 9 only AB 9 VC minus VC into VC into X, okay, times 9 minus X. So what I'm trying to write is, let us say this is X and this is X. So what is the moment about this point M at a distance X? So that is 9 VC minus VC into X. Okay. Similarly here it is 9 minus X. Okay. So you should have right. So now you can understand what is happening. So if it is 1 kilonewton, you have 9 minus X. If it is VC, it is 9 minus X times VC. That's what it is. So the same thing, you divided by EI, divide it the whole nothing by EI, and you integrate it to 0 to 9, the length of the beam or the length of the span AB. So this turns out to be uh, 243 by EI, 243 by EI into VC, because this VC is unknown. Now in this VC is upwards, okay. So sorry, the delta C dash is upwards, so this is upwards, whereas in this case it is downwards, this is downwards. So you can either write that minus this is equal to 0, or delta C is equal to delta C dash. Delta C is equal to delta C dash. In that case what happens is that 9477 by EI is nothing but 243 VC by EI. This goes off. VC is going to be 39 kilonewtons. 39 kilonewtons. Okay. So VC is an unknown. We have found out the unknown force, that is 39 kilonewtons. So what are we going to do in the next step? So the next step is to find out the rest of the forces. So we have this is 13. Let me write it in the, this is 39 kilonewtons. We have some UDL here. We also have a UDL here. This is 8 kilonewton per meter. This is 4 kilonewton per meter. Now this is 72, right? 72. So this has to balance. 72 minus 39. That is going to be, oh, 33. 33 kilonewton. What about the shear force? Will not change because there's only one resisting horizontal force, that is going to be 24, the axial force. So this will remain the same. What about the bending moment? So the bending moment is going to be 8. Let me solve for bending moment. Sorry, 72 into 4.5 plus 4 into 3. Sorry, is it 24 into 3 minus 39 into 9? So 72 into 4.5 plus 24 into 3 minus 39 times 9, that is 45. So this turns out to be 45 kilonewton meter hour. Let me write it. This is 45 kilonewton meter. So this is going to be 49. So 45 kilonewton meter. So now we have solved once we have solved for the support reactions, right? Now you can draw the bending moment diagrams, the shear force diagrams, and also if you are asked to find sorry, if you are asked to find, let us say if you are asked to find a b c, if you are asked to find delta b horizontal, delta b vertical, theta b, you can find it out, and also theta c, how much theta c can be found out, and also delta c horizontal, how much, right? So for this you need to just find, you use the unit load method, and you can easily find out what are the displacements for each type of loading. So we will also we yeah, once everything is known, right? One, see, the major part previously for the determinate structures, we don't have much trouble in finding out the support reactions, because the support reactions are directly found out by the equilibrium equations. But when it comes to the indeterminate structures, the again for the previously, the support reactions are easily found out by the equilibrium equations, and the task is to find out displacements, right? So for that displacements we have used unit load methods. When it comes to indeterminate structures, we'll make use of the unit load methods or the energy methods to find out the support reactions by the compatibility conditions. And using these compatibility conditions, yeah, once we are able to find out the support reactions, now it is again the determinate, right? Like now everything can be found out once you have the support reactions. You can find out the internal forces, the bending moments, the shear forces, the axial forces, and etc. uh, and also, if you once you have all those things, you can easily find out the displacement at each joints or each nodes, etc. Okay, so that is the only added complexity for analyzing the determinate structures. So this is one way of how to find out the unknown forces for the indeterminate structures. Again, this is basically what we are trying to do is we are trying to apply the force, and we are trying to find out the displacements, and we are trying to get a compatibility conditions there. Always we can't say that the delta A or the delta in the determinate structure and delta with the redundant forces are zero. As you like so far we also discussed about the support settlements, right? So that has to be included in that kind of a compatibility equation to find out what are the support reactions in the members. So I'll just write down the next one more question. Maybe you can solve by yourself. I'll just put on the answer for that also, because we have only another 15 minutes. 15 minutes. So I'll just write down the question there. Uh, and maybe after this question, maybe we'll discuss if there is any doubts or something. So we have a roller support, something like this, and this is W. The beam is length L, sorry, length L and EI, length L and EI. Okay, so let us call this A, B, and C. So find support reactions first, and also you can draw BMD and SFD if you are interested. Okay, so just a hint, what happens in this, let me say what all the equations do we need, what are the redundant, let me check for the static indeterminacy. So we have this is fixed roller, right? Fixed roller kind of a support. So what all the reactions do we have here? So we have bending moment M, shear force V, sorry, the axial force VA, the horizontal force HA. In this you have HC, M
C.
C.
Okay.
Okay.
So we
So
have
we have uh,
yeah. This is a
yeah,
case
this
of
is a case of again having two different two degrees of redundancy. We have
D
ds is going to be
one two
1 2
three
3 4 5
5
5
minus
unknowns,
one.
minus we have only three equations to solve it, so 2.
So two
So
are the
2 are the
degrees
degree of
degree of
static indeterminacy. So
we need
we
two
need two
compatibility
compatibility
conditions
conditions
to
to
solve
solve
this.
this kind of equation.
Okay.
Okay.
So
So what are those compatibility equations for this? So we can find out
again
again like I said, I
prefer to
prefer
use
to use
the
the
cantilever
cantilever
the
the
cantilever
cantilever
beam.
beam. So
So this is
so this is
A
one. So you this is my real beam.
this is
This
C
is C,
A
A,
B.
B.
You can
I can
you have
you
this,
have this.
you have a
You
moment
have a moment MC here,
and you
and
have
you also have
HC.
HC here.
So
So
this you
this
have
you
delta
have
C
delta C
and theta
and
C.
theta C.
For this you
For
have
this you have delta C dash
and theta
and
C
theta C dash,
and this you
and
have
this you have delta C double dash and theta C double dash.
so
So
MC and
MC and
HC you
HC
have
you'll have
two
two
compatibilities.
compatibilities. So
Delta C
delta C
plus delta
plus
C
delta C dash
plus delta
plus
C double
delta
dash.
C double dash is equal to 0.
Theta C
Theta
plus
C plus
theta
theta
dash
dash plus
plus
theta C
theta C
double
double
dash
dash.
is equal to 0.
You have two
You have two
compatibility
different
conditions.
compatibility conditions, and you can find out the answer for this.
So I'll
So
just give
I'll
out the
just give out
answer.
the answer.
You
Maybe you
can
can
try.
try.
So
So
my
my
VC,
VC,
I'll
I'm
just call
calling
it
this as
as
VC, right?
VC
VC
or
or
HC.
HC.
Let me call it
Let me
as
call it as
HC.
HC.
HC
HC is going to be equal to 0.4 WL,
and
and
MC is
MC
going
is
to be
going to be
equal to
equal to
0.23
0.23
WL square.
WL square. Okay.
So
So
what is
yeah,
the support at C?
Sorry,
sorry.
What is the support at C? Is it roller or something else?
it is a
It is a
fixed
fixed. It is a
fixed beam
fixed
with
beam with an
with a roller.
with a roller.
So
So
you can
you
have
can
a
have
free
a
degree
free
of
degree of
freedom in
freedom
vertical
in vertical
direction,
direction,
but
but
Okay.
the moment
the
is
moment is
resisted.
resisted.
The moment
The
is
moment is
resisted, but you
resisted,
can
but you
have
can
a
have a
free
free
degree of
degree
freedom
of
in the
freedom in
vertical
the vertical
direction.
direction.
It is a
It
fixed
is a
roller
fixed
kind of
roller
a
Okay.
kind of
support.
a support.
Yeah,
Yeah,
Okay.
yeah.
yeah, yeah.
So
So you have moment max. You have
bending moment
bending moment
M,
M, which is resisted, and also
the
the
horizontal
horizontal
reaction is
reaction is
also
also
resisted.
resisted there.
So you'll
So
have
you'll have
two
two
forces coming
forces
there.
coming there.
Yeah.
Yeah.
Any
Any other doubts you have?
So what is
uh,
the internal indeterminacy and external indeterminacy? Can you explain with an example?
So let me,
for
for
example,
example,
let me
let me take
take
one
one question
question
here.
here. Yeah. So again, this is kind of a. I'm just taking out. Let us say this is a frame. Okay,
We have a
we have a
frame
frame,
something like
something
this,
like this, which have the fixed ends. Okay,
fixed
fixed
condition
condition
A
A,
B
B, C,
C
D,
D
E,
E
F,
F.
G, H.
So when it
So
comes to
when it comes
external
to external
indeterminacy,
indeterminacy, right? So
external
external
indeterminacy is
indeterminacy is,
are you able to
are you
find the
able to
support
find the support
reactions or not?
reactions or not?
If you are not
If
able
you
to
are not
find,
able to find,
what are the
what are
degree
the
of
degree of
redundancy?
redundancy for that?
So now
So
you
now
just
you
consider
just
the
consider the
supports here.
supports here. So
In
supports you,
in this you
in this
have
you have
one,
one,
two,
two,
three,
three,
one, two,
one,
three,
two, three,
and you have
and you
three.
have one, two, three.
Okay.
Okay.
So you
So
have
you
three
have
unknowns, three
three
unknowns here,
unknowns
and
here,
three
and three
unknowns
unknowns
here.
here.
What are
What are
the
the
number of
number of
unknowns?
unknowns?
Number of
Number
unknowns
of
are
unknowns are
nine.
9.
Number of
Number of
equations
equations
available are
available are
three.
3.
So nine
So
minus
9
three is
minus 3
six.
is 6.
So
So
externally it is
externally it is
indeterminate.
indeterminate.
Obviously, you
Obviously,
have
okay, you
only
have only
uh,
uh, 9
9 minus
minus 3,
3,
which
which
is
is
6, which is
external
external
indeterminacy.
so this is called
External
external
indeterminacy is 6
indeterminacy is
in this
6 in
case.
this case.
And when it
And when
comes
it
to
comes to
internal
internal
indeterminacy,
indeterminacy,
what happens
what
is
happens
that
is that,
let me
let
take
me
one
take
member
one
here.
member here.
Okay, I'll take this
Okay, I'll
joint
take this
H.
joint H.
So joint
So
H.
joint H,
Let me
let me
draw
draw
it
it
here.
here.
So
So it
when I
when I cut this section
here,
here,
here, and
here,
here,
and here,
what I'm going
what
to
I'm going to
obtain,
obtain, what are my internal forces which are going to generate?
you have
You have
shear force,
shear force,
you have bending
you have
moment,
bending moment, you'll also have an axial force.
you have
You have
again
again
axial
an
force,
axial force, you also
shear
have
force,
shear force, and also you have
bending moment
bending
here.
moment here.
You'll have
You'll have
shear
shear
force,
force,
axial force,
axial
and
force,
bending
and
moment.
bending moment here.
Okay,
So again we have 3,
three and three.
3, and 3.
So we
So
have
we have
nine
9
internal
internal
forces which are
forces
going
which
to
are going
generate
to
there.
generate there, right?
But
But
you need to
you need to
understand that
understand that
these
these
forces,
forces, these three,
like whatever
like
the
what are the
forces
forces which are generated here,
this can be
this can be
solved using
solved
these
using these
forces, right?
forces, right?
If we are
If
able
we are
to,
able,
if we are
if we are
solving for
solving
these
for these
forces,
forces,
we can
we
directly
can
solve
directly
these
solve
forces.
these forces.
Okay,
Okay.
and if we
And
are
if you are
in again
again
in
in this case, in this case,
unknowns are
unknowns are
unknowns are
unknowns are
nine.
9.
Okay, we have
Okay, we have 9
uh,
unknowns.
and again
And
the
again the
equilibrium
equilibrium
equations are
equations
again
are
3
again 3
because
because
we
we
can't
can't create another equilibrium. We have only
force
force
equilibriums, right?
equilibriums, right? We have
Sigma
sigma
fx
fx
0,
0,
sigma
sigma
mx
fy
0,
0,
mx 0.
mx 0.
But
But
you need to
you
be
need to be
careful.
careful. We need to be careful in choosing this.
These are
These
actually
are
not the
actually not the
unknowns.
unknowns because
These can
these
be
can be
found out
found
by
out by
using this.
using
We
this.
just
You just
take
take
a section
a
here.
section here.
Let us say
Let us say
AH.
AH.
So you
So
have
you
this,
have this,
this, and
this,
this.
and this.
You can
You
find
can
out
find
these.
out these
You can
things. You
find
can
out
find
this
out
with the
using
help
with
of
the help
that.
of that.
You can find
You
out
can
this.
find
So
out
these
this.
are
So these
actually
are
not the
actually not the
unknowns.
unknowns.
Okay.
Okay.
So
So
the
the
actual
actual
unknowns
unknowns are only 6
internally.
internally. I'm talking about the internal
Unknowns.
unknowns.
So you
So
have
you have
six.
6.
So
So
internal
internal
indeterminacy
indeterminacy DSI, usually we name it, we call it as DSI, is 6 minus 3, that is 3.
so
So
internal
internal
indeterminacy is
indeterminacy
3
is 3
in this
in
case.
this case.
So
So
for
for
this you
this
need
you
to
need to
have
have
the external
the external
indeterminacy is
indeterminacy
6.
is 6.
Okay, the
Okay, the
internal
internal
indeterminacy is
indeterminacy is
3.
3.
So you need
So
to
you
have
need to have
9
9
redundant
redundant
forces
forces to
to
actually
actually
find
find
out
out such kind of
such
a
kind of a
problem.
problem.
The
The
reason why
reason
I'm
why
taking
I'm taking
unknowns
unknowns here
as
as
6
6
is
is
these three
these three
unknowns,
unknowns, the three
can
unknowns
be
can be
found out
found out
using
using
uh,
uh,
reactions at A.
reactions at A.
So I have
So I have
already
already
considered these
considered
A
reactions
as
at A as
unknowns in my
unknowns in my
external
external
indeterminacy.
indeterminacy.
So to
So to
find out
find
the
out the
forces,
forces,
I should
I should
have an
have an
extra.
extra. I
I
should
should
actually
have
have
six.
only 6. I
I should have
usually have a
unknowns which
unknowns
are
which are
only
only
these
these
and
and
these.
these, because this I can find out directly.
So
So again,
as a
for
thumb
as a thumb
rule,
rule, what we'll usually try to do is DS is directly found out. Like you have different support reactions. You have
minus 3
minus 3,
whatever
whatever it is. D
external.
external.
DS
DS
internal
internal
is
is usually we'll count.
for
For
example this is a
example, this
box
is a
structure,
box
right?
structure, right?
Now
Now,
let us say
let
if
us
you
say
have
if you have a portal frame. Let me just make it clear.
if you have a
If you have
portal
a
frame,
portal frame, only a portal frame.
so you have
So you
three
have three
unknowns,
unknowns here, three unknowns here.
what about
What about
internal?
internal here? Like you have 1 and 2,
One,
1, 2, 3,
one,
1,
two,
2,
three.
3.
So
So
this can be
this
found
can be
out.
found out.
Let me
Let
draw
me,
this
I'll draw this
A,
A,
B,
B,
C,
C,
D.
D.
So
So
you have
you have 1, 2, 3.
again you have
Again, you have 1,
two,
2,
three.
3.
So
So
I have
I
already
have already
considered my
considered
support
my
reactions
support
three as
reactions
my
3 as my
unknowns.
unknowns there, right?
So
So
using
using
this
this
unknowns,
unknowns, if I find out these as
these
these
unknowns,
unknowns,
I can
I can
directly
directly
find out
find out my internal forces in any all the beams.
whereas
Whereas
in this
in this
case,
case,
even though if I
even though if
find
I
out my
find out my
support
support
reactions,
reactions,
I still
I
have
still
a
have a
redundancy to
redundancy
find
to
out my
find out my
internal
internal
forces.
forces.
So that is
So
the
that is
reason
the
why
reason why we call
in
in
such
such kind of a kind of a story structures, or
in
in
such
such
kind
kind
of
of
a
a
frames
frames,
we'll also
we'll
have
also have
internal
internal
indeterminacy
indeterminacy
coming
coming
into
into
the
the
picture.
picture. Uh, is it
Is it
is
clear?
it clear or
Yeah, yeah, it's clear.
Yeah.
yeah?
I
So
think
that is the
I
Yeah.
think
yeah.
in the lectures they have mentioned it opposite because the internal indeterminacy is said as external indeterminacy. I think it is by mistake.
Okay. Okay.
Okay.
Yeah.
Yeah, yeah. Yes, yeah, maybe.
But
But this is how
usually
usually
thumb
as a
of
thumb of
rule,
rule, what we'll do is we,
if it is a
if it is a
box kind
box
of
kind
thing,
of
right,
thing,
we'll
right,
just
we'll
count
just
the number
count
of
the number of
boxes
boxes,
because
because
that
that
is
is
how
how
the
the internal
indeterminacy comes into
indeterminacy
picture.
comes into picture.
So in
So
this
in
we
this
have
we have
only
only
one
one
box,
box,
so
so
usually we
usually we
call it
call
as
it as
DSE is
DSE is,
again we have
again you have 6,
DSI is
DSI
3
is
into
3
n.
into N.
N is 1
N is
here.
1 here and
If
1.
I have two
If you
boxes,
have two boxes, right?
if you
So
have
if you have,
if this
like
is
if this
your
is
beam,
your
I
beam,
mean
I
this is
mean this
your
is your
portal frame,
portal frame,
you
you
have
have
three unknowns,
three unknown
three
three
redundancy here
redundancy
and
here
three
and
here.
3 here.
Okay.
Okay, so you have 3 times 2, that is 6 here. 6 plus 6, 12.
Okay.
Okay,
What about kinematic indeterminacy?
so kinematic is again it is similar to for example, I'll take the same frame, same portal frame. So see kinematic ones. So far we are discussing about only the reaction forces and or the forces, right? So there is also the displacements coming in the beam or the frames, right? So what are the different types of displacements or deflections happening? So this point can move in this direction, it can move upwards, and also there is a chance of rotation here. Similarly, at all the rigid joints, you can have 3 degrees of freedom. So usually we call it as 3 degrees of freedom. So degrees of freedom are nothing but the types of or the rotations or the translations that is happening at the joints. So you have 3 rotations, 3 degrees of freedom available here. This 3 here and 3 here. What about at this point? There is no degrees of freedom because it's a fixed support. It will not allow it to either translate or rotate. So 0. Here it is 0. Here it is 0. So we have 1, 2, 3, 4, 5. 5 times 3, that is 15. So 15 is my dk is what we usually mention. The static 15. 15 is my kinematic indeterminacy. So why do we use kinematic indeterminacy, static indeterminacy? Where are we going to use such kind of things? I think that we need to wait for some more time to actually understand the stiffness method. So usually we use this for the stiffness methods to formulate the stiffness matrix method. So we'll be using it. We will be using kinematic indeterminacy, and all our the codes which were written for the structural analysis, like the STAD. The STAD is actually based on the stiffness matrix method. So we'll develop the stiffness matrix. Like we have actually formulated a basic flexibility matrix, right? In a similar fashion, we'll also try to develop a stiffness matrix, and we can use. I think in this course we don't have the stiffness matrix methods. We only have an introduction to stiffness matrix method. But if you go for an advanced course of this, maybe structural analysis 2 or structural analysis 3, in that we'll be generating the stiffness matrix methods, which actually uses the kinematic indeterminacy, and then we'll try to formulate the stiffness matrix. Once you formulate the stiffness matrix, we can find out the member forces very easily. So the
So if
kinematic indeterminacy is nothing but how many degrees of freedom does the structure have? Yeah,
so if one of the support is a pin, then one more degree of kinematic
correct. Like
indeterminacy.
yeah, if you have this is a pin instead of fixed, you have a pin, so you'll have one more here. That means this is 16.
Hmm.
Yeah,
Okay.
yeah, yeah. So anything else, or shall we
Yeah,
end the
I
session?
think yeah, I don't have any difficulty for that. Okay, then thank you.